Thank you so much, Emily. And thank you so much to the organizers for having me today. I'm excited to share my work. My name's Catherine Manea. I'm a graduate student at the University of Texas at Austin. I work with Keith Hawkins, and today I'm going to be presenting, like Emily said, the GALAH view of the chemical homogeneity, lithium abundances, and ages of stellar strings identified in Gaia. So as we've seen in this conference, Milky Way structure and evolution is a major question in our field. And when we look at our favorite image from Gaia ESO of the Milky Way, along with signatures of dust and gas, we can see a lot of stars. So stars are the major building blocks of the Milky Way, and we can use their chemodynamics to inform these major questions about Milky Way structure and evolution. So young stellar groups in particular are great for probing the star formation process that builds up our thin disk. So studying the ages and dynamics of young stellar populations informs things like star formation timescales and the dynamics of star formation. And studying ages and chemical compositions of young stellar groups informs the composition of the local ISM and also mixing processes within molecular clouds prior to the onset of star formation. So stars are formed in molecular clouds, which are highly turbulent environments. And this turbulence acts to homogenize the ISM to some degree. So simulations have shown, such as Armalata et al. 2018, that molecular clouds have a characteristic homogeneity scale of 1 parsec. So it would follow that if stars are born within 1 parsec of each other, they should be chemically homogeneous. We can test this and other similar questions by observing the star formation products in our Milky Way. So open clusters and stellar associations are 2 such examples, and they've both been observed to be highly chemically homogeneous at the 0.01 to 0.07 dex level, according to several studies. And the advent of Gaia has allowed for a surge in discoveries of new young stellar groups. And today I'm going to be focusing on this one particular study by Marina Kunkel and Kevin Covey. They found a ton of substructure within our own Milky Way using HDB scan, which we heard about earlier today. So they ran this clustering algorithm on Gaia DR3 data, and they found over 1,300 newfound structures within 1 kiloparsec of the sun, and 243 of these are newfound strings. So what are stellar strings? They're elongated stellar clusters between 80 and 400 parsecs in length, and they're extremely thin. They're just tens of parsecs wide. So in this screen capture of me navigating the 3D visualization tool on Marina Kunkel's website, which is centered on the sun, and those bold lines are the local arms, you can see that these strings are dispersed all around our local neighborhood. They're believed to be primordial in shape, and they have similar dimensions to giant molecular filaments, which are elongated molecular clouds that trace spiral structure within our own Milky Way and outside of it as well. So we asked 2 major questions in this study. First of all, to what degree are these kinematically related associations chemically related? And also, what can their chemical distributions tell us about their ISM, the composition of it at their birthplace and time, and also the star formation process that produced them? So we chemically investigate these strings using 2 data sources. First of all, the GALAH survey, which is ideal for this study because of their broad chemical investigation access, and also the McDonald Observatory at the University of Texas. That part is still undergoing, so today I'm going to focus on the GALAH results. So to investigate these strings, we perform quality cuts on the GALAH data, and we cross-match it with the Kunkel and Covey 2019 catalog. And in this study, we only consider newfound strings with at least 6 GALAH sampled stars per structure. Now, this might seem like a small number, and it definitely is. However, a few studies now have drawn meaningful homogeneity conclusions from small sample sizes like these, using a particular statistical method called maximum likelihood estimation. So we model our likelihood function after those works to probe the intrinsic homogeneity of these structures. And also we emphasize that this is a real pilot study taking a first chemical look at these structures. So our final sample consists of 12 structures, 8 of which are strings. And as you can see in this XY plot, they're distributed all around our local solar neighborhood. Several of the younger ones interact with the local arm and the Radcliffe wave, which is a gas wave tracing the local arm. And the remainder lie in the inter-arm region between the local and Sagittarius arms. So again, we use the method I described earlier of maximum likelihood estimation, which we model after these works. And we compare these intrinsic dispersions in each string or structure with the two extremes of homogeneity that we can imagine. The local field, which we define as a 500 parsec cubed cube centered on each structure, and also M67, which has been shown to be a chemically homogeneous open cluster. We also probe structure age using chemistry. So the original discoverers probed ages from isochrones, and we can test or confirm these ages using chemistry. So we use lithium, which is a great indicator of age in low and intermediate mass main sequence stars, and also chemical clocks. And I'm not going to talk about the science behind these because the talk following directly mine is by an expert in this, but they're abundance ratios that scale with stellar age. So in terms of results, we find that all but 3 of the structures in our sample are generally more homogeneous than their local fields. So in this plot, I show intrinsic dispersion of the local field relative to each string. So different markers represent different strings or structures. And on the x-axis, we have various GALAH sampled elements. And as you can see, most of the strings or structures lie in this white region, which indicates that they're more homogeneous than their local field. And a few of them, however, are indeed less homogeneous than the local field in that gray region. Additionally, and interestingly, 3 of these structures are as homogeneous as open clusters in several elements. This is interesting because they're very long, so some of these are between 80 and 200 parsecs in length. So in these plots, I show intrinsic dispersion of 3 different strings versus, again, various elements. And this gray region indicates the chemical homogeneity range observed in several open clusters. And the X's are M67 sampled by GALAH. So this is a real apples to apples comparison of a chemically homogeneous open cluster in GALAH versus our strings, which are obviously also in GALAH. And so as we can see, several of these structures are extremely chemically homogeneous and approach the homogeneity of open clusters. Finally, our chemical analysis of age. We find that ages from chemical indicators support the isochronal age in 9 of the structures, but contest it in 3. So here's how we use lithium to probe structure youth, as Keith showed earlier in today's session. On the y-axis, we have lithium abundance, and on the x, we have effective temperature. So the position or the placement of these structures in this plane tell us the youth of the structure, or at least probe it. So in the background here, we have empirical lithium tracks that can help us contextualize the lithium abundance of these strings and groups. And as you can see, okay, thanks. And as you can see, when the structures are more abundant in lithium, they're younger, so that probes their youth. And for the most part, the lithium agrees with the isochronal ages in all but 3 cases. So I highlight 2 of the cases here. Thea 227 appears to be older than its isochronal age, and Thea 1376 appears to be younger. So we also use chemical clocks, as I indicated earlier, and we are able to recreate the expected trend that's linear between chemical clock abundance versus isochronal age. And we get the same results as last time. 2 of the structures stand out against this linear trend, despite the rest of them falling really nicely in line for the most part. It's the same structures that don't agree in lithium with their isochronal age. So finally, with this last 30 seconds, I want to show you what we can grasp from these homogeneity results of these groups, specifically result number 2, the 3 structures that are really homogeneous, similar to the level of open clusters. So if we pair this result with simulations, which show that the characteristic homogeneity scale in molecular clouds is 1 parsec, and also the final homogeneity of the molecular cloud tends to depend on the initial ISM homogeneity level, we can conclude that these strings and structures have 2 possible formation scenarios, specifically for those really homogeneous yet really long ones. 1, they're either born at small spatial scales and subsequently elongated somehow, or 2, they're primordial in shape, and either the ISM is more chemically homogeneous than we thought, or molecular clouds are more efficient at mixing the ISM than we previously understood. So I'll leave up my conclusion slide, and my main conclusion is the same as Daniel's conclusion, which is that chemistry is really important in studying newfound kinematic groups. Yeah, thank you.
Thank you so much. I think that's a conclusion for the conference. And I think that everybody here agrees with that. Are there any questions for Catherine? We already have one. We have a couple coming in from the chat. Okay. So Melissa Ness asks, I wonder if you have a way of differentiating between A or B in your conclusions.
Yes. So we have a few follow-up projects that we're really excited about. We're not sure if we're going to do them, but in theory, they're interesting. So we can look at dynamics of these structures, which hasn't been done yet, specifically orbital integration and whatnot, to kind of backtrack whether these elongated structures dynamically shrink when we go backwards in time, like in their primordial shape, or if they initialize as small little groups, like one of these might suggest. And another interesting thing is these structures, many of the strings are well sampled by tests. And so we were thinking it might be interesting to look at age spreads in these structures. I'm not sure if the tests, like if gyrochronology has high enough precision to really find these age spreads, but it's possible that perhaps these were born through a slow star formation process, because the ISM has been shown to be highly homogeneous for up to 300 megayears in the same spot. So these can be produced from one spot, but over time. That's just an idea. But yeah, definitely there's a lot more work that needs to be done, and also just more sampling as well.
Very cool, very cool. Melissa says thumbs up. We have another question here in the chat from, I'm so sorry if I'm going to pronounce your name incorrectly, but it's Sviatoslav Borisov. Did you consider stars from the hot side of the lithium dip greater than 6,700 Kelvin?
No, we go between 4,000 and 6,500 Kelvin, but that's a great question that someone asked last time too, and it's definitely a real concern for sure.
For sure. Very cool. Very cool. Yeah, I love the idea of integrating those orbits back in time and watching where we think those stars were however many mega year ago. Very, very cool. Any final questions for Catherine?